Okay, we are continuing week one. This is BMI 6018. I am Chad, and we just did, well, it depends on what order you're following it in. I just created this install VS Code Python on video. Now we're going to do the video for the binary content. And I've chosen this. This was new material that wasn't in the course last semester with Brian Chapman, but I feel like it's very foundational to what we're going to be doing, or just honestly the basic principles of computer science. Because the week after this, we're going to start working with data types and variables right here. In order to have a much better idea of why data types matter and what they can do, it's really important, I feel, to understand how that data is manipulated in memory in the computer to understand why data types even matter in the first place. And so the content for that is here. The book that we have doesn't really have a chapter related to binary. It sort of just jumps right into programming. So this is material I had come up with, and again, I've taught many years of computer programming courses at other universities, and then this is kind of a twist on, not a twist, it's a flavor of that lecture. But to accompany it, I wanted to point out, so we have the binary content, which I'll be going over, and then these two indentations are the supplementary material. So I just wanted to open this up and show you. This one comes from an author called Brookshire. And this is just a scan of it for the fair use policies. And this is actually really good primer on binary. So if after going through the video with me today, you still have some questions, which you probably will, give this a try. It's very good. And then also we have an ASCII map, which I'll talk about towards the end of the content. This is just a GIF of it. This is an ASCII map. You don't need to know what all this is yet. I'll get to it in the lecture, but just know that this is where that is when I refer to it. And so with that, let's hop into it. So our whole goal here is just to understand binary, how to do a few operations with binary, and why binary matters when we're going to be talking about data types next week. Again, chapter one doesn't have a ton to do with binary, but it is an introduction to some basic computer science topics. And so it would be really helpful to read that now that we're starting to get into the basic concepts. So here's going to be the content of what I go over. And again, I just wrote this just barely. But anytime you see these hashtags everywhere, that means that that's the sign for a comment in Python. So all of these things are just going to be Python lines. So you can either read it as is like this and just sort of ignore the hashtags, or know that you are welcome to, let me pin that, let's get a new window going, or know that you can open up your Python VS Code and then start working at it here. It's not good, oops, sorry. It's not going to it's not going to show the syntax until it's labeled as until it's labeled as a Python file. Sorry, that's just the simplest way. So that you can decide. So I'm going to open up the folder we did for the last assignment. I'm going to go, I'll just do it right here. It really doesn't matter. So now you can sort of get the Python coloring going on here. I'm going to jump to the top. So again, the hashtag is the indicator that this is a comment line in Python. So it ignores those and turns them green. So it won't try to compute them, whereas these ones you can see are colored and it will try to execute that. There's only a few lines in here of processing, not a lot. I was just trying to illustrate a couple of things. And I can say, if you're familiar with, if you come from any biomedical field or computing field, or if you've used Python before, which you probably haven't if you're taking this course, but what you're seeing here is like narrative coupled with code, and then I'm also going to be showing you the output. There's a whole tool called Jupyter Notebooks that's basically designed to operate this way, and it would so you It's meant to disseminate research. And so we're foregoing that at the beginning of the course. We're trying to just get you into the basics, understanding the concepts and the syntax, and keeping it simple. And then in the latter weeks, I think it's maybe the second to the last week of the course, or even maybe the third to the last week, we will introduce Jupyter Notebooks. So I already typically like to do a format similar to that. This isn't in Jupyter Notebook format, but just know that what you're seeing here is kind of in that format, and we'll be getting to it later. Okay. Oh, one other thing. So I put links to it. This is the Brookshire binary PDF. I didn't put a link to this on there, but it would be good to do. This is honestly one of the best things I've found about binary. It can come across a little daunting, especially if someone is a little obtuse in explaining it. Whereas this is a teacher who was trying to explain it to 5th graders or maybe 4th graders. It's been a while since I've read this. But he's using the Socratic method. I don't know if you're familiar with the Socratic method, but it's self-discovery. So he's asking these 4th and 5th graders just common sense questions that they would know the answer to. And each of those questions is building up to honestly how binary works and how binary was developed. And at the end of this, if you read this whole thing from top to bottom, he has all the same questions and stuff. He gets to the point where it explains, and he gets the kids to understand how binary works, why it's a thing, and how to compute with it. And I thought it was very, very well done. And I wish I could put together something like this for all my lectures. This is really, really nice. It's a little bit of a read, and if you understand binary enough, you don't need to worry about it. But again, I would highly recommend doing this, maybe even before, maybe stop the video and go do that first. Anyways, it's very well done. Okay, so we're going to go through this, and honestly, it's going to be mostly just, I'm going to add in some stuff here that the video adds that we don't have in the content, but it's basically going to be a retelling here of this. So currently, when we talk about numbers in society, if someone says, "How old are you?" It's a number. I just turned 40 last weekend. So someone asked me, "How old am I?" I would say I'm 40. When we're talking about these numbers, these are represented in base 10. And if you don't remember back to grade school or high school or wherever we learned about these things, I wrote out why it's called base 10. Another word we call is decimal. Deci means 10, so these are all base 10 numbers. And all we do with base 10 is, or why it's called base 10 or decimal, is that reading from right to left, so the right of a number is the smallest, and as we go left, it gets 10 times bigger than the number before it, and you keep going left and left and left, and the number keeps getting 10 times bigger, and that's why it's called decimal or base 10. So just something like, I said I'm 40, and so we would read from the right, because this is the ones column right here, and then times that by 10, this is the tens column, and then we could even go bigger. Right, this is the hundreds column, right? So each of these is 10 times more. We add those up and comes up with the whole number. I guess I could have just read my instructions here. We have the same thing. So for 11, and then for 765, we wrote it out. And the actual formal notation for this are these sort of lines right here. And this is how we have agreed to represent our numbers. So we start on the right. And then we have a base, so how many numbers are possible, and we have 0 through 9, right? So there's 10 choices. We raise it to the exponent of how many times it's used. We start with the 0 first, and then as we increase it to the left, we add an exponent. And then we would sum those up. So we have 1 times 10 to the 0 plus 1 times 10 to the 1, right? So we know 10 to the 0 is a 1, so we have 1 times 1 is 1. 10 to the 1 is 10, so we have 1 times 10 is 10. So we have 10 plus 1 is 11. So that's the formal notation for base 10 or decimal. And then here's just another illustration with a third spot. So again, we're saying we have 5 in the 1 spot. So we have 5 times 10 to the 0. We're going to increase the exponent right here. We're going to say, oh, we have 6 of these things, 6 times 10 to the first. And now we're finally going out to the hundreds, and we're going to say we have 7 times 10 to the second power. So that's 100. So 7 times 100 is 700, plus 6 times 10 is 60, plus 5 times 1 is 5. So we're saying 700 plus 60 plus 5, and that's 765. Okay. So this isn't binary. This is just explaining to you how we currently do it. So you'll see that it's not such a big shock in how we do it in binary. What's important to know here is we're breaking them down. We're taking the number of units in that column and we're multiplying it by our standard notation. And the standard notation is saying we have 10 choices, how many options of numbers we have, and that's 0 through 9. And then we just increase the exponent. So we have 0, 1, 2, 3, 4, 5. It would go on, ad infinitum, however many you had. And then we just sum all those numbers together. We add them all up, and that's how we get our number. Okay, so binary, we're going to do the exact same thing. Except the only difference here is we're not using base 10 like we do in decimal. We're using base 2. And that's why we call it binary. There's only 2 choices in computers. They only know how to turn things on or off. So we get a 1 or we get a 0. Those are our only choices. And so then if we look here, this is the same sort of thing, but this is in binary instead of in decimal format. So we would start to the right and work our way left. And now we're base 2. We're not base 10, right? So we're not decimal, we're binary. There's only 2 choices instead of 10 now. So we have 2 choices. We raise it to the exponent. We always start with the 0, and then we increment it by 1, and then increment by another. So we have 2 to the 1, 2 to the 0, 2 to the second, 2 to the third, and we keep going on. 2 to the fourth, 2 to the fifth. Does that make sense? And then the only other difference is up here when we're doing, when decimal, we're saying how many of those things in that column are there, right? We had 5, 1s, 6, 10s, 700s. Binary works a little bit different in that either it's there or it's not. It'll either be a 1 here or a 0 here. And I should probably show you that here in a second. I'll do another one with some zeros. So we're saying we have one of these items in the first spot, we have one of these items in the second, one of those in the third, and one of those in the fourth. And if we calculate those out, we're saying 1 times 1, because that's what 2 to the 0 is 1. And we're saying what's 1 times 2 to the first? That's a 2. What's 1 times 2 to that? It's a 4. And then that's an 8. And then again, just like we did up here, once we did that math, we added them up. We had a 700 plus 60 plus 5. We add those all up to get 765. Same exact thing we do here. We have a 1, we had a 2, we had a 4, we had an 8. We add those all together, and we get 15. So that's a really quick, brief view of it. This is code we can run that will show you the binary equivalent of them. Hang on one sec. Okay, so right here, oops, where did we go? Right here. So I'm having this right here. So I just wanted to show you what these numbers look like. So again, we read from the right to the left in binary. So it's a little bit different because in decimal we read sort of from the left to the right. So right here, so there's other code showing here, so ignore that, I guess, because that's further down. But it's these first 2 lines right here. So I'm saying 15 in a base 10 is equal to this in binary. So this is what it would look like in binary. And it's all 4 of those items turned on. And that's exactly what we did right here. This was our 15 calculation lines, 35 and 36, where we're saying all of these items are turned on. And that's what the 1 means. It means something is turned on there, and we should count it. We can turn things off, and this is how we get the different values in there. So we could do, we'll just say this one's turned off. So there's no item in that column. And again, if you're times anything by 0, it's going to be a 0. So we're doing all the same things. We're saying in the first column, we have a value there. Remember, it's binary. It's either there or it's not. Whereas in decimal, you can say a number like 7 of those or 5 of those or 6 of those. We're just saying there's one of those things or 0 of those things, because again, it's binary. So we're saying we have one of those things here In this one, we don't have anything there, a 0, and then we have one of these things, and then one of those things. And again, we would add them all up, and then this is going to be 13. And this is 15. And I can show you that really quickly. I'll just copy that, and then we'll just say 13 right there. If you're looking at this code, it may be confusing. Maybe not. It's very, very simple. All we're saying is we're going to print to the screen a string, which is what's in quotations, this text string. And then we're going to do, we're going to call a method called bin. And all bin does, if I hover over it, it says right here, it returns the binary representation of an integer. So I'm going to pass in these integers, and it's going to send me out the binary equivalent. And then so we're just showing it onto the screen. I'm going to hit save. I probably got to restart Visual Studio because I did that. And let's run this bad boy right here. There's going to be other stuff showing up because there's more code here. But if we look up here, now you can see our 15 is 1, 1, 1, 1, which is what we did right here, right? We had 1, 1, 1, 1, and all those things turned on and summed equal 15. But now we're talking about 13, where we turned off this second spot right here. And Python agrees with us. It's 1, 1, 0, 1. So we have one of those, none of those, and one of those. And so now you can see we can start doing this to get any combination of number. Just to show you what the key looks like here, to have something to map to. It's 1, 2, 4, 8, 16, 32. And the idea with binary is everything doubles. Oops, should be 5. Oh, 2, 5, 6, 5, 1, 2. So the idea here is each time we add a bit to the left, it doubles the value to the right. Whereas in decimal, it times it by 10. Remember, because it's what decimals do. We are doubling. So we're not timesing by 10, we're timesing by 2. And so we go from the right to the left. And so if I were to overlay these numbers, the 15 would look like this. Oops, I need to just make that a comment. So we have 0, oops, we have 0 of those, 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 1 of those, 1 of those, 1 of those, 1 of those. And that's how we get 15. Okay. And then if we wanted to do the 13, this is just a different way of showing you the exact same thing. We have none of all of those, but we do have one less of those. And so now that's how we get 13. And this is how we're starting to build up our binary. And now, and so if we go further left and left, the numbers just double, and then we would have to pick up these little bits over here to the right. So the example of 765, I can copy this, and then here's what Python said the output of binary for 765 was. That's what the 0b in front of it means, by the way, is binary. There's other ones. It can be 0x for hexadecimal. If you don't know what that means, it doesn't matter. You don't need to. And there's 0o for octal, which is, so hexadecimal is base 16. Octal is base 8. We're doing binary, and obviously there's decimals. There's a lot of different encoding schemes, so don't get hung up on this. The same principles apply to all of them. So if you understand the decimal one, and now you're starting to learn about binary, then the exact same rules apply, and you can do hexadecimal and octal and all those things, but we won't cover any of that in this course. I was just explaining what the 0b means here. So we ignore the 0b. That's just saying this is encoded in binary. Okay, and then so to get the 765, so this is the bigger one. We're saying we've turned on this spot all the way over here, which is a 512. We've turned on this one, which is a 128, a 64, 32, 64, and so on and so on. And when we sum all of those together, it equals 765. So when you see all these ones and zeros like this, don't be overwhelmed or confused by understanding that. All you got to do, or see like something like this, really long, like the 765, you just got to put this key underneath it that gets incrementally bigger from right to left. and then just add those values all up. Additionally, you could do the full notation, which is the exact same thing. I'll put it under here. It's not going to line up very well. Let's turn that into a comment. But I just want to show you a little bit. Just trying to make these all very similar here. Right, so it's the same thing as saying that. Oh geez, everything's going to get poorly aligned again. Is that. Shoot. Let's just do this last one here. So pump that 2 over. And then I'm just trying to show you that these. There we go. No. There we go. Okay, so there's more to it, but for the first 3, right, you take the 1 that it gives you, or the 0. You could put the mapping key under it, or if you prefer, you can do the full notation for it, and then you would just keep going, right? So we got 0, or 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 4, 5, 6, 7, 8, 9, 10, whatever, however many spaces you need to represent the number that you have. And that's, okay, so that's what we're doing here. Just reading ahead to make sure I didn't skip anything. In fact, I think I did jump quite a bit ahead, but we got the same content that you were going to see right there. Yeah, so if what I just explained didn't make sense, and it might not, because we went through that really quickly, read those 2 links, look at the Brookshare, especially these 2 pages, 42 and 43. It does a really good job. I feel like this is fairly clear, especially if you have any background in math, but if it's still not clicking for you, check the Brookshare or shoot me an email, chad.hodge@utah.edu. Or if I don't respond quickly enough, you can always reach out to the TA. Or you can just go into Python and start monkeying around with putting in decimal numbers and converting them to binary, and then just seeing what happens and see if it makes sense to you. And so work with that until it does. You don't have to be an expert at it, but you need to understand what you're seeing when you do see it. And that's what I'm saying right here. It's fairly important, at least when we start getting into data types and when we start talking about storing data to the computer, reading data into memory. All these things come into effect. And I don't know if I talk about it later on, so I'll just say it now. No, I'm going to save it for the data types. Yeah. Okay, so we need to make sure you've understood everything up here, which there wasn't a ton, but make sure you understand that. And then so just a couple of vocab words. You probably already know what these are just from life and living around computers, but just to formalize what these are. We have a bit and a byte. And sometimes they're used interchangeably. They definitely should not be. So when you see a binary thing like this, let me copy that. Just to give an illustration here. Get rid of those. Okay, so when you see something like this in binary, or when you're talking about encoding a value in binary, a single item that you're storing, either a 1 or a 0, is considered a bit. It's just one thing, and it can be only 2 values, a 0 or a 1. That's a bit. You group these into sections of 8, like this. So this grouping of 8 bits is called a byte. 8 bits, not bytes, 8 bits. And we do this for a few reasons. Just going to try to map that out, but that might be too big. Here, I'll just try it really quick. I want to show you what the key for that would be, just to place underneath it. So we have 1, 2, 4, 8, 16, 32, 64, 128, 256, 512. How many is that? 1, 2, 3, 4. Oops. 4, 5, 6, 7, 8, 9. So we got 1, 2, 3, 4, 5, 6, 7, 8. So 128. Okay. So when we have something like 8 bits, just trying to line these up for you to understand a little bit. Okay. So we group 8 bits into what's called a byte. There's one even higher, which isn't very common. It's called a page. And a page is 8 bytes, which is 64 bits. So make sure you see that this is different. So this is talking about 8 times 8 is 64 bits. Pages aren't used very often other than operating systems deal with pages. At least Windows operating systems do. Let's turn this one on too. Okay. So the idea here is how much are these equaling? Let me find my calculator. So we have, if we've turned these all on, our 8 bits, our 1 byte, we have the equivalent of 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1, 255. I don't know if 255 means anything to you, but in the computer world, a lot of things have a maximum value of 255. Things like hex codes max out at 255 because they're using 8 bits or 1 byte. But all this is saying is if we have 8 bits or 1 byte, the highest number we can store in that is 255. And this is important, and we'll talk about it a little bit down here. So I want to make sure we get to it at the end right here. Yeah, let me just put a link to that. I'm just going to copy that down really quick. So we're going to need that here for our last portion of this, which is the ASCII stuff. Okay, so just know that the bit and the byte, what the difference is with them. So if you're talking about things, make sure you're using the right word. When you see operating systems, it will be 64-bit or 32-bit. It is not 64 bytes and 32 bytes. Those are very different things. There's a Nintendo 64, for example, that's 64 bits, not 64 bytes. Also know, or maybe not know, it's anecdotally interesting to know. When you go by memory, like RAM for your computer or, I don't know, CDs if they still make them, or jump drives, thumb drives or whatever, they'll give you numbers of how much memory they can hold. I don't know if you've ever wondered before, but they go in increments, 64 megs or gigs or whatever, 128, 256, 512, they go up like this. And I don't know if you've ever wondered, but like you're not going to go from 124 megs or gigs of storage to 1025 or 1026. It's because the way binary works, if we have one more memory addressable space, it effectively doubles our memory. So as the materials get smaller, the physical materials, I used to work at Micron producing semiconductors, so I feel a little knowledgeable on this. But as we get more space available to store more things, we're going to start doubling or quadrupling, and they go in the orders of 2, right? So when we first started making memory for computers, it was probably like 8 megabytes. And then as we got those little transistors smaller, it jumped up to 32, and then we got them smaller. It jumped up to 256 megabytes or gigabytes or whatever the case may be. But it's going to always be in one of those increments, and that's why. So if you see those numbers, just know that it has to do with binary and the way that information is stored in the computer. And so you can imagine what the next one would be in the sequence after 2048. Hopefully you can see it in your mind already. It's going to be 4096 because that's double. Okay. So just a side little tidbit, which I think is interesting. And it has to do with how much data it can store, and how much data it can store has to do, or directly translates to what it can actually do, what your program can do, and how quickly it can do it, and how many of those things it can do. And so it's really important, and the bigger the number, the more operations, the more data, the more values it can store. And so this is just sort of a side little tangent I spent too much time on, but it's interesting to me. Okay, so now we're storing this data. So say we have the number we want to store, we'll just say 255 in this case because I already have it written right here. Say we want to store the number 255. We can see here that we're going to need 8 bits to do it. Right here, right? So we're going to need 8 bits to store 255. But what we're not seeing here is how do we represent things like a negative number? What if I wanted to store a negative 255? How the heck are we going to do that? There's a concept in binary called 2's complement, or complement notation. Sometimes you'll just see it as, honestly, anything, just the word complement. Applies to when applying it to binary, at least. There's a paradigm of how data is stored and read. You have to have rules applied to it, right? So we understand the computers just write zeros and ones. It's up to us as programmers or the operating system or interpreters to know once we're reading those zeros and ones out of memory, we have to apply rules to read it in the right order and to do certain specific things. Otherwise, it's just ones and zeros. So we have to have a layer of abstraction that means something to us. So we've all agreed with this 2 complement notation thing. And again, this isn't something you're going to have to do. The operating system and the interpreter and the compiler and all those things take care of these for us behind the scenes. But it's important when we're talking about data types, I think. In order to store negative values or positive values, we have 2's complement notation. And all that is saying is it takes the very first bit, or the biggest bit, and it reserves that for a sign, either a plus or a minus sign. So for example, if we're trying to store 255, we know that that's going to take these 8 bits, but they actually need one more over here, 256. And this one is going to be representing not a number. So the very leftmost one doesn't represent a number. It's going to represent the sign, the plus or minus. So if it's on, it might be positive or it might be negative. We'll say in this case it's a negative, right? So if this is turned on, then that means that this is a negative number. And if this is turned off, if that's a 0, like this, that means it's a positive number. It might be reversed, but as long as everybody agrees on what it is, it doesn't matter. So the point is we need an extra bit of space, or double the amount of bits here, in order to represent a signed number. So when we're coming up with how we want to store things, and we'll talk about this more data types, we need to understand what the range is of numbers or of things that we're going to want to store, and then properly size things to make the most efficient use of our data within the system. So imagine we are writing software and we have a patient come in, or we need to write software, I should say, that stores a patient's age. Maybe that may not be the best thing because we probably store their birth date and not their age, but let's just say for the sake of argument that we're storing their age, and the patient is 40. So we got to think about what the domain of the possible values are for age. For example, we're not going to have negative numbers. And as soon as I say that, I can think of exceptions to it, because I've done a lot of software for the NICUs, and we do a lot of tests on babies who are not born yet and are typically, or technically I should say, are technically not even born yet, so they are less than 0. Although we don't refer to them that way, we would refer to gestational age, which is a positive number. So when we're talking about ages, it's only going to be positive numbers, right? Either after you've been born, from birth till whatever, is a positive number, or from gestation, what's your positive number for that? So we're not going to have negative numbers. We're not going to have a zero. And honestly, what's the human lifespan? 120, 150, 200. It's a very small set of numbers we need to store. We need to store between 1 and, I don't know, 200. Let's say we have some medical advances in the future, right? 200, 500, I don't know. So it's a very small range of numbers, right? And so in order to store those, we don't need 8 whole bits to do it, or 9 in this case, right? So we can say we don't need to store positive or negative because we already know there's never going to be a negative. We know that 255 is probably too much. We could just do right here, we could do all of these numbers, which would be 128, all these combined. We can say 128, and to do that, we're just going to need to store 1, 2, 3, 4, 5, 6, 7 bits of memory for a patient, right? So we can say the 128 is going to be 7 bits. And that's really efficient. And it's important for us as programmers to think about that stuff because the default in Python, other languages are different, like C# and Java, you can get a lot more specific. Excuse me. In Python, it tries to do some smarts behind the scenes, which ultimately take up more memory. They're treating memory as cheap, but it's not. So they're going to do 32 bits as their basic standard for storing a number. And so how many values can you store with 32 bits? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. That's a whole heck of a lot of numbers you can store there when what we were talking about before is just 7, right? 1, 2, 3, 4, 5, 6, 7. So that's all we would need to store a person's age, right? And so all of this is wasted space. These will never be turned on. These will always be zeros, but their memory that's being held in RAM, you know, in our memory for when our software is running, or on the hard drive if we've persisted it. It's a lot of memory that's being wasted. It's more than triple, quadruple, right? It's like 3 or 4 times more than the actual number we're storing is just being wasted. And so this is the whole point I wanted to make with the binary lecture is when we're careless with the data types that we're using, with how we define data and how we operate and do calculations with data, we can be really expensive behind the scenes and not even know it because again, and Python is sort of adding to it, it's treating memory as cheap. And in this case, it's cheap, right? We're talking about 32 bits. That's almost nothing. And when we're talking about a single patient, not a big deal, right? We can do that. The problem comes in when we're starting to do big data. And Python is used for some big data stuff, or it can be. So say, for example, like I work at Intermountain Healthcare. I've done, for one of my aims in my dissertation and just for other daily stuff, we'll do cohorts, right? We'll say Intermountain has 30 years of records, and that's something like 12 million patients. So now imagine I'm doing this, everything times multiplied by 12 million, right? So now it's 7 bits times 12 million, or 32 bits times 12 million. I did equals, I should have done times, right? Oh, not divide either, the times. So you can start to see we're going to get into wasted space really quick. All this stuff wasted times 12 million, that starts to get to be an issue. That starts to affect the throughput that we can do, the maximum amount we can do before like our system crashes, we run out of memory. We have all sorts of issues. And so as developers, it's our job to be vigilant keepers of memory and data of our computer, to be efficient, and to make sure just how we do that, how we would manifest to that is by choosing the proper data types. And again, Python is a little bit of a culprit here because their smallest number type is 32 bits, which I'm showing here. Other languages like Java and C# and some of the slightly older languages, I don't know if older is the right word, just different languages, they let you pick if how many bits and bytes you want your numbers. You can do a 1 bit, which would be a Boolean. You can do a 4, an 8, a 32, a 16, a 64. And you can really get into it. So we don't have as much control over it here, but I wanted to point that out because we do have Python. When it sees that a number is getting too big, it'll automatically switch and upgrade you to a 64-bit number. And so just to illustrate that, it's this big and this much space. So if you're not careful, you can be tying up 64 whole bits of space. Trying to line these up. 64 bits of space instead of just the 7 that we need. And that's almost a factor of 10 now of wasted space by not choosing the right data types, by not performing our operations correctly, by not understanding the range of numbers that we're going to have to be dealing with for our specific problem. Okay, and then the leftmost bit in all these cases, back to the original point, is the complement bit here. And that's just going to handle the sign, the plus or the negative. That's what we're dealing with here. And yeah, I was just going to show you this here. So if we are dealing with 32 bits, like I showed you here, this is the default in Python for a number, 32 bits. What's the maximum number that you can store in here? So if all these are turned on, what's the maximum we could store? And again, that number is right here. It's 4.3 billion, 4.2 something billion. That's the maximum number. But since we're saving one spot for the plus or minus sign, instead of being 2 to the 32nd bit, we're 2 to the 31 bit, which effectively cuts down in half the number we can store, down to 2 billion. But again, this is less of an issue with Python. It's just pointing out that we save that 1 bit for the plus and minus, and doing so cuts our numbers in half somewhat. I wanted to point this out. Even though it is 2 to the 31 in this first bit is for positive and negative, and we think we're cutting our numbers in half, we're actually keeping the numbers the same. We are still able to store 4 billion in change in numbers. It's just that half of them now are going to be above the 0 line, and the other half are going to be negative. So we are spanning. We still have 4.94 billion numbers. It's just only half are positive and half are negative. So we didn't lose a ton in what the range we can do. We did in how much could be positive or negative. So it's important to notice, maybe less so in Python. And then when we get a number like this, if we think, I mean, this is a really big number. Unless you're doing scientific computing, you're probably not going to run into numbers bigger than this. But if you do, just know that in Python, it'll automatically convert you up to a 64-bit variable space, and then you get, again, double that number. And then after that, it'll just start using as much memory as you have available to it. If you go above, what would that be, 8.6 billion in numbers, it'll start going beyond the 64, and we'll start tapping into the memory that you have available. And there really is technically in Python no upper limit of numbers to use. Okay, so all that. Now we're going to switch gears here and go into fractions for binary. We want to store things that are less than a whole number. Everything we've seen here is how do we store whole numbers, right? How do we store my age of 40? How do we store 2 billion or whatever? But what do we do when we want to do partial numbers, right? Because even though I'm 40, I'm not technically 40. I'm 40 in some part of a year, right? I'm like 40.02 if you want to get technical about it. Or 40 and, what is it, like 5/365ths, whatever that is. My birthday was like 5 days ago. So 40 and 5/365ths, whatever the number is. So how do we store data that's not a whole number, not an integer? And these are called floating numbers. Anytime we have fractions and we need some sort of precision, they're floating point numbers compared to the integral numbers that we had up here, the whole integers. And it's almost the exact same thing. I'm going to skip past some of that, and we're just going to go right here. We're doing the exact same thing like we saw before with the full notation. The difference is we have a dot, and then anything to the right is a decimal, and in this case, we raise the exponents to a negative number. So instead of going 1, 2, we go -1, -2, -3. So each spot gets successively half the size instead of double the size. You'll remember, hopefully, from your math days that anytime you raise an exponent to a whole number, we're sort of doubling it. But when you raise it to a negative number, you're putting that number in the denominator. And so it's just 1 over. Right, it's going to be a fraction 1 over 4 instead of just 4. That's what the negative is doing for us. So here's the example here. So we want to store 5 and 5/8. 5 and 5/8 equals 5.625. So how would we encode that in binary, or what would that look like sort of in the full notation? So we put the point here. And just to point out, we don't use, you might be tempted to call this a decimal point, but again, we're not working in the decimal number system, we're working in the binary number system. So we use the more general and more specific radix point. So if you're working a binary, this is called a radix point, not a binary, or sorry, a decimal point. But I'll forgive you if you call it a decimal point. It's a radix point though, just for your nomenclature. So the same thing we were doing before. So we want to store the 5, right? So we got this 5.65. So the whole numbers are stored to the left. The fraction of numbers are stored to the right of this radix point. So we need to store this 5. So how many of these things need to be turned on to get the 5? So we have the 1 is turned on, the 2 is turned off, and then the 4 is turned on. So it's 4 plus 0 plus 1, that's 5. You can see that right here. 4 plus 0 plus 1 is 5. And then we want to do the fraction. We want to get this 625 over here to the right. And then so 1 times 2 to the minus 1 is a half. And then this would be 1 over 4th and 1 over 8th. That is actually a typo right there. Right, so it's a half is turned on plus nothing plus an 8th. And that's going to give us 5/8, because this would come out to 4/8 plus that is a 5, so that's 5/8. So that is how we would store 5 and 5/8 using binary. One of the other things we might want to do is addition. There's a few reasons we do this. In computer science and in programming, there are things called bitwise operations where we do math and do checks just at the bit level. That's one reason we need to understand how binary addition works. We won't be touching that in this course, but we will want to understand adding numbers together, what is happening in this behind the scenes with our binary data when it's storing and reading it in memory, in RAM. And so I just set up a little trivial example here, but just to illustrate for you, I'm going to add 8 and 11 together. And what I wanted to do here is show you what the binary representation of 8 was, what the binary representation of 11 was, and then what the binary of 8 plus 11 looks like. And then we'll look at the rules really quick. These are the rules right here. So what we're talking about doing is we're going to write the number 8 in binary, so it's right here. So ignore the 0b. So we have 1, 0, 0, 0, 0, right? So let's say we have the 1 is turned off, the 2 is turned off, the 4 is turned off, and the 8 is turned on. So this is 8. And then likewise we're doing for the 11. So it's 1, 0, 1, 1. So the 1's turned on, the 2 is turned on, the 4 is turned off, the 8 is turned on. So 8 plus 2 plus 1 is 11. So we have 8 plus 11. We know in our mind what 8 plus 11 is going to be 19. And this is the representation of it. So I'm just trying to show you what it looks like lined up. It's not like super lined up. Let me super line it up for us. Yeah, it keeps coming down here to the bottom. I keep hitting run and I don't see anything happen down here, and that's because I forget it keeps appending it down here to the bottom. So if you want to get around that issue, you can just, every time before you run, just hit clear output right here. That erases what was there in your output. Hit play or debug, whatever you want to call it, and then your output comes right here. And so now these are better lined up, still not exact. The 0Bs are lined up, but the other ones aren't. So the idea here is we add them just like we do in, if we've written this out in arithmetic in like 3rd grade, right? So say we had 1,000 plus 1,011, we would do the whole carrying the one thing, right? We'd say 0 plus 1 is 1, 1 plus 1 is whatever, 2, right? And we'd carry the numbers, and then the result would be underneath it, right? So we're doing the same thing here, except we have different rules in binary. And since there's only 2 numbers, there's only a few different permutations we can have, and so this is really easy. So anytime we're adding a 0 and a 0, meaning the top number is a 0 and the bottom number is a 0, like in this case right here, we get a 0. Anytime one of the numbers is a 1 and the other is a 0, the answer is always going to be a 1. So that's what we have here, a 1 and a 0. And then anytime both numbers are a 1, we get a 10, which is essentially just doubling the number and shifting it left, which is what's happening there. So just to do this in our mind, we have a 0 plus a 1, we see as a 1. So we've dropped that down. This isn't quite lined up. Let me see if this is going to line that up a little bit better. Save that, clear that, run that. It's thinking, there we go. Okay, so now the right-hand sides are lined up instead of the left-hand sides that I had. Okay, so 0 plus a 1 is a 1. And again, a 0 plus a 1 is a 1. 0 plus a 0 is a 0. And then 2 ones. A 1 plus a 1 is a 10. So we have an extra bit involved. And so this is going to be the binary for 19, and this is how you get the answer. And there's another way you can do binary addition. This is the tried and true way by hand. There's a much simpler way that would require humans. This is the way that we do with computers. If you're involved as a human, you can just do these things in your mind, right? You know 8, you know 11, you know it's going to equal 19, so then just convert 19 into binary. You don't need to go through all the steps of zeros and ones. You know it's already going to be 19, so just go figure out what binary of 19 would be. That's easy. Okay, and then the final thing to talk about here really quickly is all we can do in binary is store numbers. I hope you're seeing that. What we do with those numbers is going to be different based off what sort of rules we're imposing on it. For example, I've already described that 2's complement notation, where even though we're storing 1s and 0s, we've already applied this abstract rule saying, all right, this very leftmost bit is going to be the plus or minus, and figure that out and apply it and include that in the output. But what we haven't talked about is how the heck are we going to store other things besides numbers, right? Because most of the things we would want to store, thinking of a patient at Intermountain Medical Center, for example, is we're going to have words, right? We want text, letters, right? The doctors are going to have notes that talks about the diagnoses of the patient. None of those are numbers, right? That's all text. How are we going to store text? And so again, everybody has to get together and agree on a paradigm, on a schema here that we're going to be using. And one of the things that or the way that we do that is, at least the way it started out, is there's something called ASCII. And what does it stand for? American Standard Code Interface Interchange or something like that. And that was this picture over here. Right here. There we go, ASCII. ASCII is just a scheme that everybody's agreed to. They said, okay, so in the English language, and this is why the A stands for American, and I'll talk about that in a second more. This is saying for all the English letters in the English alphabet, what are all the characters we would have to deal with? And also, what are some of the invisible characters we would have to deal with, like spaces and nulls and backslashes and stuff that keyboards would need and computers would need. And we came up with them. And it turns out there's about 128. The number 128 should be very specific and significant to you. We just talked about that, 128, because everything in binary is incremented doubly so, right? So where did it go, right? So we had I don't remember where it went. But we get, like with the operating system, yeah, right here, right? So we go 32-bit, 64, 128, 256, so 128, right? So it has to fit within one of those numbers, this key, this table. When we came up that we were using 128, that's 127 plus this first one, which is 0, 128 characters or control sequences or commands or whatever you want to refer to them as, things that we would need to know for American alphabet and for computer usage in America. And then we've said, okay, so all we need to do now is say, I want to store a C for Chad, a capital C no less. I want a capital C for Chad. And all I got to do is store in decimal. That's what these are: decimal, hexadecimal, octal, and then HTML equivalents. And this is the character. So for the capital C character, I need to store number 67 decimal value in binary. So I got to convert this 67 to binary, store that somewhere that I'll be able to retrieve it. And then when I pull it back, I will know that that's text encoding as a C. It's not the number 67, it's the character that maps to this 67. And that's what ASCII is doing for us. And likewise, if I wanted to do a lowercase h, starting to spell out Chad, I would store the number 104, right? And so you can see to do this, we only need 8 bits to store that, because that 8 was giving us 255. So that's all we would need. Probably 7 actually would store this. So we don't need a lot of space. We've all agreed on what those numbers mean, how to do it and retrieve it, and we're golden. To add to that though, that doesn't work very well internationally. I used to work for a company called Micron, and even in Hewlett-Packard, I should say, was a real issue. I worked at Hewlett-Packard. For a few years, I wrote printer firmware. And I worked on a large enterprise printer. It was codenamed the Nozomi, and it was for a Japanese market. And you can imagine that none of this stuff works in Japanese. They have the kanji alphabet, which is thousands of characters, right? I think there's over 2,000 characters in kanji. We have the 26 plus our numbers. They have something like 2,000 and something plus whatever. So they need to store a whole heck of a lot more data than just the American alphabet does. And to solve that and to go international, there's a different, more expansive standard, which I didn't link to, but it's called UTF-8. It's universal something format, text format or something. And so trying to find an image of that. But it stores, these just giving me ASCII, I want UTF. The point is that UTF is the same thing, but it's international, and it's probably not showing it because there's so many, but it stores 2096. The 2096 limit was where it was at. Yeah, all these are giving me is the ASCII one. I want the hex one, or the UTF one. And there's probably not an image for it because, again, there's over 2,000 of them. I saw something quickly. Yeah, that's frustrating. Anyways, you can go Google that up. Just know that for international stuff, there's UTF. And again, we're not going to do any of that stuff in the class. I'm just trying to give you a more complete picture of what we're talking about, so we're not so America-centric. And so that's the idea. That's how we would do it. And that's the idea. And so one of the questions in the quiz is converting binary to a number and then converting that number to a letter to encode a string. So all the stuff we talked about before has that, and then this ASCII map is what you'll need to complete that last portion. I think there's just 1 or 2 questions on it, but that question is worth a lot of points because there's more work involved with it. And that's it. And that was a pretty high level overview of binary. But make sure you understand this. Again, shoot me or the TA questions, but reading the material, the chapter, and then that one web link, the Brookshire chapter, and then that web link about the Socratic method that the guy did for the 4th and 5th graders should get you through it.